A modern AI accelerator can execute an astonishing number of operations every second. But that headline number hides a basic problem: the compute units cannot work on data they have not received. When model waits, activations, or the key value cache arrive too slowly, expensive tensor cores wait. The GPU is powerful, yet the system behaves like a supercar connected to a narrow fuel line. That is why the real ceiling on AI performance is often not the number of arithmetic units. It is how much data the memory system can deliver, how quickly it can deliver it, and how efficiently the package can move that data into the processor. This is the role of HBM high bandwidth memory, and it is becoming one of the most important constraints in the entire AI hardware stack. The simplest way to understand the problem is the roofline model. Every workload needs two resources: computation and data movement. If an algorithm performs many operations on each byte it loads, it can approach the processor's compute ceiling. But if it performs relatively little work per byte, its speed is capped by memory bandwidth. Adding more tensor cores does not remove that cap. It simply makes the processor capable of becoming idle faster. This is the memory wall. Peak flops describe what the chip could calculate. Memory bandwidth helps determine how often the chip can actually reach those calculations. The distinction matters because AI workloads are not uniformly compute-bound. Large matrix multiplications can reuse data and keep arithmetic units busy. Other stages repeatedly stream weights and cache data from HBM. The same accelerator can therefore move between compute-bound and memory-bound behavior within one request. The practical ceiling is the lower of two limits: peak compute, or memory bandwidth multiplied by the workload's arithmetic intensity. That is why a balanced AI chip needs compute, memory, packaging, networking, software, and power delivery to scale together. HBM attacks the bandwidth problem by changing the physical shape of memory. Conventional memory devices place packages beside the processor and communicate through relatively narrow interfaces running at high clock speeds. HBM stacks multiple DRAM dies vertically. Through silicon vias create thousands of short electrical paths through the stack, while an extremely wide interface connects the stack to the accelerator through an interposer or another advanced package structure. The result is not simply faster DRAM. It is a much wider data highway located extremely close to the compute dies. Three measurements must remain separate. Capacity tells us how much data fits beside the accelerator. Bandwidth tells us how much data can move each second. Latency tells us how long an individual access takes. HBM's defining advantage is bandwidth, although capacity and energy per bit are also crucial. HBM4 doubles the interface width from the previous generation to 2048 data connections. Micron states that its 12-high, 36GB HBM4 stack delivers more than 2.8 terabytes per second. The wider interface is the central idea: move more data in parallel, without relying only on extreme pin speeds. Training a large model creates several simultaneous demands on memory. The accelerator must hold model parameters, intermediate activations, gradients, and optimizer states. It must also exchange data across many GPUs. Capacity determines whether a model, batch, or sequence length fits. Bandwidth determines how quickly those tensors can be read and written during forward and backward passes. When capacity is insufficient, engineers use model parallelism, activation checkpointing, offloading, or smaller batches. Each workaround introduces communication, recomputation, or scheduling overhead. When bandwidth is insufficient, compute units wait for tensors to arrive. Higher bandwidth can increase utilization, but only when software exposes enough parallel work and the rest of the system keeps pace. Precision also changes the equation. FP8, FP6, FP4, and other compact formats reduce the bytes moved per operation, raising effective arithmetic intensity and increasing the amount of model data that fits in memory. But lower precision is not free. It requires suitable kernels, scaling methods, numerical controls, and workload support. HBM therefore interacts with architecture and software. It does not independently create performance. It removes one of the most expensive constraints so that compute can be used more consistently. Inference makes the memory story even more visible. The first phase, called prefill, processes the input prompt. Large matrix operations can make prefill relatively compute-intensive. The second phase, autoregressive decode, generates tokens one at a time. During decode, the accelerator repeatedly reads model weights and accesses the key value cache created by earlier tokens. NVIDIA describes typical LLM decoding as bandwidth-bound, while prefill is often compute-bound. As context length and concurrent users increase, the key value cache consumes more capacity and creates more traffic. This is why memory capacity affects how many sessions can be served, while bandwidth affects token throughput and latency. The economic consequence is direct. An accelerator with enormous theoretical compute can still deliver poor cost per token if memory traffic prevents high utilization. Techniques such as quantization, grouped query attention, cache compression, paged attention, kernel fusion, and speculative decoding attempt to reduce or hide this traffic. But every optimization is measured against the same physical question: how many useful bytes must move for each token, and how quickly can the system move them? HBM sets a powerful upper bound, while software determines how closely real applications approach it. HBM also turns packaging into a system-level technology. The memory stacks must sit close to large logic dies, connected by dense wiring across a silicon or redistribution layer interposer. TSMC's CoWoS platform integrates multiple system-on-chip dies and HBM stacks specifically to deliver high compute performance and memory bandwidth. As packages grow, the industry must control interposer size, routing density, power integrity, signal integrity, warpage, thermal stress, bonding quality, and test coverage. A defect in one expensive component can threaten the yield of the entire package. That makes known good die testing, advanced inspection, thermal materials, substrates, and assembly equipment economically important. Power is another constraint. Moving data consumes energy, and HBM stacks sit beside processors operating at hundreds or even more than 1000 watts. The package must deliver current without unacceptable voltage loss and remove heat without damaging stacked memory. This is why the HBM bottleneck cannot be separated from CoWoS capacity, substrate availability, test capacity, cooling, and system design. A memory supplier may produce good HBM dies, but accelerator shipments still depend on successful qualification and high-yield integration into the final package. Current accelerator specifications show how quickly memory has become a competitive axis. AMD's Instinct MI350 series offers up to 288 GB of HBM3E and 8 TB per second of peak memory bandwidth per accelerator. NVIDIA's Blackwell generation also operates around the multi-terabyte per second level, and its rack-scale systems aggregate hundreds of terabytes per second across many GPUs. The next step is HBM4. Samsung announced commercial HBM4 shipments with a sustained transfer rate of 11.7 gigabits per second and capability up to 13 gigabits per second. Micron says its HBM4 provides more than 2.8 terabytes per second per stack and more than 20% better power efficiency than its HBM3E counterpart. NVIDIA's Rubin architecture goes further by combining HBM4 with new controllers and tighter compute memory integration, targeting up to 288 gigabytes and as much as 22 terabytes per second per GPU. These numbers are not directly interchangeable because product configurations, stack counts, precision modes, and system designs differ. But the direction is unambiguous. Compute growth is forcing capacity, bus width, bandwidth, packaging area, and power efficiency to rise together. For investors, the useful question is not simply whether HBM demand is strong. It is where qualified, profitable output is constrained. First, watch customer qualification. HBM is customized around specific accelerator controllers, package designs, thermal limits, and reliability requirements. A nominally fast device has little value until it passes qualification and enters volume production. Second, watch yield across the full stack, advanced DRAM dies, TSV formation, stacking, base die integration, interposer assembly, and final test. Third, watch bandwidth and capacity per accelerator rather than only total memory bits. A shift from HBM3E to HBM4 changes interface width, base die complexity, packaging requirements, and value per unit. Fourth, watch advanced packaging capacity. TSMC explicitly identifies CoWoS as a foundation for AI products that combine logic and HBM. Fifth, watch test, inspection, substrates, bonding equipment, thermal interface materials, and liquid cooling. These are not automatically equal beneficiaries. Their earnings depend on market share, qualification, pricing, utilization, and capital intensity. Finally, separate announcements from shipments. Samples, qualification, volume production, package output, and recognized revenue are different milestones. The strongest signal is not a press release. It is rising qualified output with stable yield and improving economics. HBM is not the only limit in an AI system. Some workloads remain compute-bound. Others are restricted by GPU to GPU communication, network congestion, software inefficiency, kernel launch overhead.